Welcome to the debate. Today, we are dissecting a framework that, well, it claims to solve the single most frustrating paradox in modern engineering. We're looking strictly at the Complex Product Development Model, or CPDM, from Christer Sandahl in Lund, Sweden.
It is a dense piece of work, very ambitious, and it tries to answer a question that, frankly, keeps most of us up at night.
The central question is posed right at the start of Chapter 2, and it's haunting, really. Sandahl mentions that the very text editor he used to write this book, a product with decades of industry evolution behind it, crashed over 200 times.
Which cost him weeks of work. I mean, it's a familiar pain, right? You buy the premium software, the high-end hardware, and you still end up staring at a frozen screen.
But think about the implication there. We have been building products for centuries. From the Pantheon in Rome to modern skyscrapers, we've mastered the physical world. Yet in the world of software and integrated electronics, we just accept failure as standard. Why do products fail to satisfy users despite massive investment? Why does scaling up an engineering team so often slow things down?
Yeah, it's the billion-dollar question. And today, we're framing this discussion specifically for mentors who are speaking to senior engineers. We're not here to simplify things for novices. We are here to see if we can connect the why, the theoretical background on complexity from the opening chapters, with the how, which lives in the rigorous, and I mean rigorous, glossary of the CPDM.
I'm taking the position that CPDM offers a necessary paradigm shift. I believe that without the extreme precision found in those glossary definitions, we are just guessing. We are trying to build skyscrapers with the tools we use for summer cottages. The only way out is through what Sandahl calls intellectual control.
And I'll be taking the skeptical view. I agree with the diagnosis, we are drowning in chaos, but my concern is whether the cure, this massive glossary, this rigid hierarchy, risks introducing its own kind of friction. I worry about what the book itself calls artificial complexity. Are we actually solving the problem, or are we just bureaucrating it? Because for an agile team, this looks heavy.
A fair challenge. But let's start with the root cause. According to the source material, our failure isn't due to incompetence or, laziness. It's an exploding number of market opportunities and technical possibility.
The sheer volume of choice, we can do anything, so we try to do everything.
Exactly. Look at the Pantheon, built 2,000 years ago. That was the cutting edge of complexity for its time. Today, a mid-sized construction company could build it pretty easily. But a modern skyscraper? That requires hundreds of disciplines, high-tech materials, intricate systems.
The scale is changed, obviously.
But it's not just scale, and this is the first key insight from the background chapter. Sandahl writes, 1 + 1 = 3. When quantity increases, quality changes. You hit a tipping point where your old methods don't just work slower, they stop working entirely. That is the moment a paradigm shift is required. You can't use a slide rule to design the Beijing Bird's Nest Stadium. And you can't use messy, informal development styles for complex integrated products.
Okay, I'm with you on the problem statement. The 1 + 1 = 3 concept is valid. Complexity isn't linear, it's exponential. But let's talk about the solution.
The solution is intellectual control. Now, I want to be precise here because this is our first critical glossary term. CPDM defines intellectual control as a result so well described that developers understand that it is correct by only inspecting it.
By only inspecting it. That is an incredibly high bar. You're saying I shouldn't need to run 1,000 unit tests or do a trial assembly to know it works?
Ideally, yes. The description, the architecture is so clear, the logic so tight, that inspection reveals the truth. If we don't have that, we're just throwing code and mechanics at a wall and hoping it sticks. That is not engineering. That's trial and error. And trial and error is fine for a hobbyist maybe, but not for a medical device or an autonomous vehicle.
It sounds like nirvana. But let me push back from the trenches. The source material describes a complexity dead end. It uses the n-body problem from astronomy to illustrate this. When you have 2 planets, the math is easy. When you have 3, Sun, Earth, Moon, it took centuries to solve. You add more, you get chaos. Sandal defines unmanageable complexity as something whose further development is unpredictable because it has turned into something that can no longer be sufficiently understood.
Which is exactly what we see in legacy code bases. Every single day. You touch one module and something completely unrelated breaks.
Agreed. But there's another danger lurking in that glossary. Artificial complexity. The definition is stinging. Complexity caused by incompetent usage of a sufficient model or correct usage of an insufficient model.
A crucial distinction.
My fear is that by forcing mechanics, electronics, and software into one rigid, holistic model, we might be creating that artificial complexity ourselves. We might be the ones adding the confusion. When I look at the glossary, black box, white box, nesting levels, formal scenarios, I wonder if we're building a machine so heavy it can't move. Are we suffocating the distinct, fluid nature of software by trying to treat it like a building?
I don't think we're suffocating it. I think we're finally giving it a skeleton. But let's dig into that fluidity argument. You mentioned the solar system analogy. Let's look at the geocentric versus heliocentric debate that's in Chapter 2.
The classic shift. Earth in the center versus the sun.
Right. In the medieval geocentric model, with the Earth in the center, astronomers had to invent epicycles, these spheres within spheres, to explain why planets sometimes moved backward in the sky. It was a mess. It was artificial complexity created by humans because they had the wrong fundamental model. The math worked, kind of, but it was hideous.
And Copernicus fixed it by putting the sun in the center, simplified the model.
Exactly. He didn't just tweak the math, he changed the center. Sandal argues that modern product development is full of epicycles. We patch code. We add wrappers around broken systems to hide the bugs. We create workarounds for hardware. That is all artificial complexity. CPDM claims that if we understand the intrinsic complexity, which is defined as complexity by nature, which cannot be reduced, we can strip away all that man-made confusion.
That is a compelling argument. I see why you think that. But have you considered that the CPDM glossary itself might look like epicycles to a software engineer? I mean, look at the definition of intrinsic complexity. It says it cannot be reduced by models so far. That implies humility. But then the model demands we define everything as a black box or a white box. It demands we classify every single interaction. Is that simplification or is it just categorization?
It is simplification through categorization. Because without classification, you have the summer cottage. This is the most devastating image in the book, and I think every senior engineer listening will recognize it.
It's certainly vivid. The cottage that grows like a tumor.
We've all seen it. You start with a small cottage, a simple app, a basic prototype. You need a new bedroom, so you tack one on, then a kitchen extension, then a porch. Years later, you have a labyrinth of nooks and corners and leakages. There's no continuous living space. Sandal writes that software often looks exactly like this summer cottage.
Yeah, I can't argue with that. We call it technical debt, but summer cottage, that implies a structural rot that's harder to fix. It implies the foundation was never meant to hold the weight.
And you cannot fix a summer cottage by painting the walls. You have to understand the structure. And this is where the glossary becomes a weapon, not a weight. This is where the connection between the why and the background chapter and the how in the glossary is tightest. We need to understand the difference between a black box and a white box.
Okay, let's parse those definitions. Because in Agile, we talk about transparency. Hiding things sounds counterintuitive.
It's not about hiding truth. It's about hiding complexity to allow focus. A black box is defined as an element which conceals all of its inward content, but shows its dynamic behavior via its interfaces. This is crucial. You don't need to know how the fuel injection works to drive the car, but, and this is key, it can be opened to become a white box.
And the white box is defined as an element which is an open black box containing disclosed architecture ingredients?
Precisely. The problem with the summer cottage is that there's no distinction. Everything is just stuff. A variable over in the kitchen affects the plumbing in the bathroom. In CPDM, we have a black-white box hierarchy. We have nesting levels. Level 0 is the environment. Level 1 is your product. Level 2 are the subsystems. If you don't strictly define these levels, you aren't engineering. You're just nailing planks together.
I see the value in the hierarchy. The glossary definition of nesting level Location of a black-white box in a hierarchical product structure is clean. But here's where I get skeptical. In the physical world, a wall is a wall. It stops the wind. In software, boundaries are fluid. I can punch a hole in a software wall in 2 seconds with a pointer or a public variable.
But should you? That's the point. The model isn't about what you can do, it's about what you must do to maintain control.
Let's talk about the Vasa, the Swedish warship from 1628. Sandahl uses this as the ultimate example of impossible principles.
A tragic example. The king demanded more cannons, more features than the ship's architecture could support. He wanted a double gun deck on a hull designed for one.
And it sank in 10 minutes, less than a mile from the harbor. But Sandahl uses this to critique model management. He talks about the principle of decoupling. Managers love to say, let's decouple the organization. You 5 go work on the engine, you 5 work on the sales.
But if the ship itself isn't decoupled, the organization can't be.
Exactly. The text says, few managers understood that if the product wasn't partitioned in parts, it was useless to partition the organization. This is Conway's law in action.
And this is why the glossary emphasizes interfaces, but not just interfaces in some vague sense. CPDM distinguishes between a connection interface and a boundary interface.
I did find that distinction interesting. Usually we just think of an interface as a plug.
A connection interface is the means for 2 or more elements to influence each other. That's the plug. But a boundary interface is the means for 2 or more elements to keep apart.
That keeping apart is what would have saved the Vasa. If they'd had enough ballast, it's the bulkhead.
Exactly. If you don't define the boundary interface, your subsystems bleed into each other. You get the summer cottage. My argument is that unless you enforce these definitions, unless you write them down and respect them, developers will naturally break the boundaries because it's faster in the short term.
But defining a boundary interface in a Word document or some CPDM spec doesn't enforce it in the code. This is where I worry about the paper-tiger aspect of CPDM. We can have intellectual control on paper, but does it translate to reality?
It translates if you treat design items with respect. The glossary defines a design item as material desired granularity formal enough to be orderable. Whether it's a screw or a subroutine, it has to be orderable. You have to be able to say, build exactly this.
And that leads us to the biggest friction point, the unification of disciplines. Mechanics, electronics, and software.
Sandahl is very clear here. Software engineers often claim their material is immaterial. It's just thought stuff. It doesn't follow the laws of physics.
And to an extent, that's true. I can change a line of code in a second. I can't change this steel hull of a ship in a second. Software is malleable. That's its greatest strength.
But that flexibility is a trap. Sandahl argues that because software is immaterial, it is much easier to hide poorly constructed programs than, for example, to hide an ugly wall in a house.
That's a fair hit. We do hide our ugly walls behind APIs.
He says we need to visualize software just like we visualize a circuit board. We need a physical architecture defined as a drawing illustrating how ingredients physically appear, and a logical architecture, a drawing illustrating how ingredients logically relate to each other.
I'm sorry, but I just don't buy that a physical architecture drawing of code provides the same value as a blueprint of a house. Code is dynamic. It flows. Trying to freeze it in a drawing feels archaic.
But it lives somewhere. It lives in files. It lives in memory. The glossary defines source file and header file explicitly. If you don't structure your source files, the implementation, and header files, the interface, with the same rigor as you structure a gearbox, you end up with the summer cottage. You end up with a monolith.
Okay, let's define monolith.
The glossary defines monolith as an often huge element that can be handled only as a whole, since its content have no evident interfaces or its evident interfaces are unmanaged.
I grant you that. A monolith is unmanageable. It is the definition of a complexity dead end. When you touch one part, the whole thing shakes.
Exactly. The definitions of structured versus unstructured programs are useful here. The idea that a structured program prohibits the go-to instruction, that ultimate chaotic jump, is fundamental. But CPDM goes further. It wants us to define stimulus history, wait states, use units. Stimulus. Based on the wait state, you don't have engineering. You have magic, and magic crashes text editors.
Magic is just science we don't understand yet, but point taken. If we want 99.999% reliability, we need clockwork behavior. I suppose my resistance comes from the fact that modern software frameworks handle a lot of this state management for us.
They handle it, but do you control it? Or is the framework doing the driving? Intellectual control means you know.
Let's circle back to that 1 + 1 = 3 concept. The paradigm shift. We're talking to senior engineers here. They know how to code, they know how to design circuits, but do they know how to integrate them without creating a wassa?
That is the challenge. Sandel suggests that without a shared language, without this glossary, we're just shouting at each other. One person says interface and means a graphical user screen. Another means a copper wire.
And the glossary clarifies that a user interacts through a man-machine interface, but a connection interface is between elements.
Right. Precision matters. When a mechanic talks to a software engineer, they need to agree on what constitutes a component.
I will concede this. The definitions of design item versus component are illuminating. A design item is the spec. A component is the approved item after verification. We often mix those up. We start building with things that are just sketches.
And that leads to artificial complexity. We're building on quicksand. If you don't verify that the design item becomes a component before you stick it in the product structure, you are guessing.
Okay, let's look at the implementation. The glossary isn't just a dictionary, it's a toolbox, as shown in the source imagery. But tools have weight. If I have to define every black box requirement, white box solution alternative, and environment interface before I write a single line of code, am I moving too slow? In a market that changes every week, can I afford this level of intellectual control?
You're moving slowly at the start to move infinitely faster later. Remember the text editor that crashed 200 times?
Hard to forget.
That software company likely moved fast. They ignored the white box definitions, they broke things, and now the user is paying the price. CPDM asks us to pay the price upfront, to achieve intellectual control before we build.
To realize that CPDM is correct by just studying it. It's a high bar.
It is. But consider the alternative, the summer cottage that keeps expanding until it collapses under its own weight.
I suppose my hesitation comes from the fear of the geocentric trap again. Are we building these perfect spheres of definitions, nesting levels, black box weight states that don't actually match the messy reality of the market?
The market is messy. The environment nesting level 0 is chaotic. But the product level 1 doesn't have to be. We can build a black box that handles that chaos predictably.
I like that distinction. The chaos is outside. Inside, we need order.
Exactly. And that is what the glossary provides. It gives us the terms to enforce that order. When we say encapsulation or information hiding, we aren't just using buzzwords. We are using the black box definition to save us from ourselves.
I think we've reached the crux of it. The complex product development model is not for the faint of heart. It's for those who have hit the wall.
The complexity dead end.
Yes. If you're building a simple website, maybe this is overkill. Maybe it is artificial complexity for you. But if you're building a medical device or a car or an integrated system where lives or billions of dollars are at stake,
then you need a paradigm shift. You need to accept that what got you here, heroic coding, informal sketches, verbal agreements, won't get you to the next level. You need to embrace the rigor.
I'll agree with that. The wassa didn't sink because of bad wood. It sank because of bad architecture and a failure to understand limits. If CPDM acts as the ballast, the architecture ingredients that keep us stable, then it's worth the effort to learn the language.
That is all I'm arguing. We need to stop guessing. We need intellectual control. We need to know the difference between a black box and a white box as intimately as we know our own names.
And we need to ensure that our pursuit of that control doesn't turn into a bureaucracy that stifles innovation. We need to use the toolbox, not let the toolbox use us.
A fair warning.
So, to the senior engineers listening, you're the mentors now. You've seen the crashes. You have lived in the summer cottages.
Take a look at the CPDM glossary. Treat it not just as a list of words, but as a set of tools to dismantle the artificial complexity in your organizations.
Decide for yourselves if your friction is intrinsic, part of the problem, or artificial, part of your process.
There is always more to explore in the material. The background chapter sets the stage, but the glossary writes the script.
Indeed.
Thank you for listening to The Debate.
Until next time.